The purpose of this lab is representing the floating tape experiment in which the amount of charge on two tapes was measured experimentally and computationally by treating the tapes as point charges. Creating a more refined model by simulating the tapes as one-dimensional lines of n charges and comparing the value for the overall charge of the tapes obtained with each model. The main physical principles involved in this lab are Newton's first law and second law, the gravity near its surface, as well as the electric charge, Coulomb's law, and the electric field by a thin rod. By collecting the experimental data and through hand calculations and a computational model, the charge on the tapes was estimated to be roughly 25 nanocoulombs. This model is likely to replicate the experiment and estimate the value for the charge more accurately. However, it could still be significantly imprecise as it makes some simplifying assumptions that could generate calculation errors. In the experiment, two pieces of tape were stripped off a third piece of base tape. The two strips acquired positive charge while the base tape acquired negative charge. The first piece was let floating from two separate supports and left to calm due to gravity. The second positively charged strip was placed below and brought close to the hanging tape. The separation between the tapes at which the electric force and the force gravity of the hanging tape were balanced was measured. Knowing the separation and the mass of each strip of tape, the magnitude of the charge of each tape was estimated assuming the strips of tape behaved as point charges. In the setup, the system is a floating tape, while the main elements of the surroundings are the bottom tape, which exerts a repulsive electrostatic force on the system, and the earth, which exerts a gravitational force on the tape. Modeling the tapes as point charges, the force balance equation is: we measured that the forces were balanced at a separation of 25 centimeters. Assuming that the tape had a mass of 1 gram per meter, the mass of a 0.2 meter strip of tape is 0.2 grams. Plugging in these values, the estimated charge of each tape is roughly 11 nanocoulombs. Using this value for the overall charge on each tape, we now divide the tapes into one-dimensional pieces of length dl and with charge dq. The charge density of the tapes is the overall charge over the length of the tape. With the charge density, we can calculate the charge on a single piece of tape. We can build a model that divides the tape into 100 smaller point charges instead of having to consider infinitely many chunks. By doing so, we take a piece of the floating tape and compute the net electric field and the electric force on this piece by adding up with the contributions of all 100 chunks on the bottom tape. In the model, some constants as well as objects and initial conditions are set. Then, a function for the electric field of point charge at an observation location is defined. After that, two lines of 100 charges simulating the tapes are modeled. Then, the tape objects are defined and some scale factors are set. Now, the electric field contribution for each piece of the bottom tape on each piece of the top tape is computed. Knowing this, the electric force on the top tape is also calculated. After that, the errors for the electric force and the gravitational force are created. Finally, the results are printed. The model with one-dimensional lines of charges yields a charge of roughly 25 nanocoulombs. Some sources of error include that the tape is modeled as a 1D strip of tape. In reality, the electrons are ripped off from all over the tape, which causes the charge to be distributed over the tape's area instead of over its length. The simplifying assumption can make the actual and calculated values differ. The assumed values for the charge on the tapes and from the separation at which forces on the floating tape are balanced are likely often the real value due to measurement and simplification errors, generating deviation on the obtained values for electric field and force. Also, the amount of chunks on each tape might be large enough to provide a reasonable estimate for the electric field and force, but for more precision, the numbers of subdivisions of the tape should be further increased. Recall that if we model the tapes as 2-point charges, the estimated charge on the tapes was 11 nanocoulombs compared to the 25 nanocoulombs obtained with the 1D line of charges model. The main cause for the difference between the estimated electric charges on the tapes is due to the assumption made on where the charges are located. If all the charges at a point, the magnitude of the charge is smaller. However, a one-dimensional line of infinitesimal charges provides a better estimation for the electric force as it takes into account how the charge is distributed over the tape. This model yields a charge magnitude more than double from the point charge model, showing the significance of the underlying model assumption. The hanging tape experiment was replicated with a more complex model. The charge obtained with the refined lines of charge models varies significantly from the point charge model, resulting in a 2 times larger value for the charge on a single tape. The lines of charge model still could have some errors, as some experimental measurements might be inaccurate, and there are still ways to improve the model, such as making 2 or 3-dimensional tapes or increasing the number of point charges forming each tape. This experiment shows the effects that assumptions have on physical models and experiments on their results. While in some cases a very simplified model might suffice to give a rough estimate for a value, in other cases it is necessary to use a more complex model that resembles reality better.